Hi, this is Alex from devstories.eu, Python, Cheminformatics, and AI, Episode 8 of 22. Computing complex substructures across a massive dataset can easily crash your machine with out-of-memory errors unless you know exactly how to manage your data footprint. The technique that resolves this is high-performance cheminformatics. When you extract features from a molecule, you often use substructure-based fingerprints. The Kleckner-Roth fingerprint is a classic example. To compute it, your machine checks a molecule against thousands of predefined chemical patterns, known as sparse patterns. It scans the molecular graph over and over to see its specific functional groups or structural motifs exist. Doing this sequentially for a few molecules is fine. Doing it for a dataset of 400,000 molecules is a severe computational bottleneck. The computation of molecular fingerprints is an embarrassingly parallel task. The structural analysis of one molecule has absolutely zero dependency on the analysis of the next molecule in your dataset. Because they share no state, you can compute them entirely simultaneously. To scale this effectively in Python, you utilize Joblib, specifically relying on the Loki executor. When you initiate the process, the input dataset is split into chunks corresponding precisely to your available CPU cores. If you have a 16-core processor, your input molecules are divided into 16 separate batches. Each Python worker process takes one batch and begins executing the sparse pattern matching independently. The technical hurdle with multiprocessing in Python is usually the cost of moving data between the workers and the main process. Loki bypasses this by using memory mapping. Instead of serializing the final fingerprint arrays and sending them through inter-process communication, the workers write directly to a shared memory space. For computationally heavy fingerprints like Kleckner-Roth, distributing the workload across 16 cores yields nearly a 15-fold speedup. That handles the processing time. The second critical bottleneck is system memory. A single Kleckner-Roth fingerprint vector is long. If you process hundreds of thousands of molecules, you generate a massive matrix of results. By default, numerical libraries return this result as a dense NumPy array. Every single position in that matrix allocates memory, regardless of whether the value is a 1 or a 0. Chemical fingerprints are overwhelmingly sparse. Usually, only 1 or 2% of the requested structural features are actually present in any given molecule. The vast majority of your resulting matrix consists of zeros. Storing those zeros is what triggers the out-of-memory errors on large datasets. The fix is switching the output format to a SciPy sparse matrix, specifically using the compressed sparse row format. A sparse matrix fundamentally changes how the data is stored. Instead of building a rigid grid in memory, it only records the values of the non-zero elements alongside their row and column coordinates. Consider a real-world scenario using the PCBA dataset, which contains just under 440,000 molecules. You run the Kleckner-Roth fingerprint computation across the entire dataset using your 16 cores. The parallel execution finishes efficiently. If you leave the output as the default dense array, this single matrix will consume just over 2 gigabytes of RAM. By instructing the computation to return a SciPy sparse array instead, that exact same dataset drops to just 23 megabytes. You achieve an 88-fold reduction in memory without losing a single piece of chemical information, and the sparse representation does not negatively impact your computation time at all. Here's the key insight. You do not need a massive compute cluster to process hundreds of thousands of molecules, provided you stop paying the memory tax for storing zeros and ensure your data passing skips standard inter-process communication overhead. That's all for this one. Thanks for listening and keep building.